In this video, we're going to use the node voltage method to find for the voltage VO, which is the voltage across this 4K resistor. Now, because we're going to use the node voltage method, the very first thing we should do is identify all of our essential nodes and choose one of those nodes as our reference node. So we know this is going to be an essential node. I'm going to label this node 1. We know this is an essential node. I'm going to label it node 2. We have another essential node right here. Okay, so I'm going to label this node 3. And we have one more essential node at the bottom here, but I'm just going to take this essential node to be our ground node. Okay, so let's start to write node voltage equations at each node. Now, for node 1, we know in this particular branch, we just have a 6-volt source, which means right away we know the voltage at node 1, and that's going to be the value of the voltage at the source, which is 6 volts. Therefore, we can say the voltage at node 1 equals a positive 6 volts because of the polarity, right? Okay, now that we know the voltage at node 1, we actually can just move on to the voltage at node 2, right? So we want to find the voltage at each node. That is the plan. So let's write a node voltage equation for node 2. Now remember, we're always going to assume the current is leaving the node, okay? So to find the current in this branch, we're going to take the voltage difference, which is going to be V2 minus V1 over 6,000 plus, we have the current flowing in this branch. To find the current in this branch, we're just going to divide the voltage by the resistance. So we're going to have V2 over 12,000 plus, now when we look at this, we have a current that's going to go this way. But look what's in this branch. We have a branch that's going to be separated by 2 essential nodes, and it has a voltage source in between those 2 essential nodes. Now it's important for us to recognize if we know the voltage at any of those nodes. For node 2, we don't know the voltage at node 2, and for node 3, there is nothing that's going to tell us what is the voltage at node 3. Therefore, we're going to have to perform the supernode method because you have a sole voltage source in between 2 essential nodes and you don't know the voltage of any of those essential nodes. So we're going to perform a supernode. So I'm just going to ignore this 6-volt source and I'm actually going to move on to node 3. So instead of finding the node voltage at node 2, I'm going to say node voltage at supernode, because we have a supernode now, right? So now we're going to assume the current is going to go this way, and this way. We won't worry about this right here for now, because we know we have a voltage source there, so there's nothing we can do. We're just going to act like that doesn't exist for the time being. So we're going to say, to find the currents going upward, we're going to take the voltage difference. So that's going to be V3 minus V1 over 4,000 plus, we're going to have the current flowing in this direction. That's going to be the voltage V3 over 12,000 plus, we have a current flowing in this direction here. We know the current flowing in this direction is going to go through both of these resistors, and the current will be the same. Therefore, we can say V3 over 2,000 plus 4,000. Okay? Now all of that equals 0. Okay? So all of that is going to equal 0. I'm just going to circle this for now. We know V1 equals 6 volts. Okay? Alright, so now that we have this, let's start to simplify this. We're going to have V2 minus V1 over 6,000 plus V2 over 12,000 plus V3 minus V1 over 4,000 plus V3 over 12,000 plus V3 over 6,000 equals 0. Now that we have this, we can get rid of the denominators by finding the LCD. So we're going to multiply each term by 12,000. So when you do that, for the first term, we're going to get 2v2 minus 2v1 plus v2 for the second term. For our third term, we're going to get 3v3 minus 3v1. For our fourth term, we're going to get v3. And for our fifth term, we're going to get 2v3. And we know 12,000 multiplied by 0 is just going to give us 0. Okay, now that we have this, we're just going to simplify this now. We're going to have a negative 2v1 and a negative 3v1. So when we combine that, we're going to get negative 5v1. Then we have 2v2 plus v2. So that's going to give us plus 3v2. Then we have 3v3 plus v3 plus 2v3. That's going to give us plus 6v3 equals 0. We know the value of v1. We just found that. That's going to be 6 volts. So we're going to substitute 6 everywhere we have v1. We're going to have negative 5 multiplied by 6 plus 3v2 plus 6v3 equals 0. When we simplify this now, we're going to get 3v2 plus 6v3 equals 30. And this is going to be equation 1. Okay? So we have the node voltage equation at this supernode here. And this is going to be equation 1. Because we had a supernode, we must have a constraint equation. So the constraint equation is going to be between those two essential nodes that had the voltage source between them, which is going to be node 2 and node 3. Now, according to the polarity of this voltage source, because the positive terminal is closer to node 3, we're going to say that node 3 has a higher potential. So we're going to say node 3 has a higher voltage than node 2. Therefore, because the polarity is running positive to negative, we're going to say V3 minus V2 equals 6 volts. Okay? So for the constraint equation, we're going to have V3 minus V2 equals 6. So this is going to be equation 2. Now when we look at this, we have two equations and two unknowns. Therefore, you can use simultaneous equations or the matrix method. I'm just going to use the matrix method. I'm going to do it right here, actually. So I'm going to have a 2 by 2 matrix. We know we want to find V2 and V3. Okay? So when we do this now, we know for our first equation, we have a positive 3 and a positive 6. And that equals 30. For our second equation, we have, let's just rewrite this real quick. We're going to write V2 in front. So we have negative V2 plus V3 equals 6. So we're going to have a negative 1 for V2 and a positive 1 for V3. And that equals positive 6. So we're going to take the inverse of A, multiply it by B. When you do that, V2 equals negative 0.67 volts and V3 equals 5.33 volts. So we found the voltage at node 2 and the voltage at node 3. Okay, now that we have this, let's go back up with our question. They want us to find the voltage VO, which is the voltage at this 4K resistor right here, right? So when you look at this, it's very interesting what's going to happen at this particular point. Now there's a few things we can actually do here. We can take a KVL loop at this loop right here, right? We can take a KVL at that loop. We can also find the current flowing through these two resistors, because we know the total voltage is going to be V3, so we can find the current. And once we find the current by saying V3 over 6,000, then we can then multiply the current by this 4K resistor to find the voltage VO. And another way we can solve this problem is because we have two resistors in series, and we know the total voltage that's going to be passing through these resistors. To find the voltage across one of these resistors, we can actually just use voltage division. So voltage division is probably going to be our easiest way to solve this particular problem. So that's what I'm going to do, right? We should remember the equation for voltage division. It's going to be the voltage they want us to find equals the voltage source multiplied by the resistor of the voltage they want us to find divided by that resistor that they want us to find the voltage at plus the second resistor. Okay, so let's write that down really quickly. So we're going to have VO, which is the voltage they want us to find, equals VS multiplied by RO divided by RO plus R1, right? Let's start to fill this out. VO, which is the voltage they want us to find, equals VS, which is the source voltage, right? So we know the source voltage is going to be the total voltage in this particular branch. Now we don't know the voltage at this 4K resistor or this 2K resistor, but we know the voltage at node 3. If we know the voltage at node 3, this is going to be our source voltage, because this voltage at node 3 is going to be the sum of these two resistors' voltages. So we're just going to write the voltage source to be V3, which is the voltage at node 3, multiplied by, we have R0, that's going to be the resistor that's going to have the voltage VO, so that's going to be a 4K resistor. So we're going to have 4,000 for the numerator, and then for the denominator, we have R0 plus R1, that's going to be 4,000 plus the second resistor is a 2K resistor, so that's going to be plus 2,000. Okay, now we can simplify this further. We know VO equals, we know V3 is 5.33 volts, so we're just going to write 5.33. So this is going to give us 2 over 3, right? Now when we put this in our calculator, VO equals 3.55 volts. So this is going to be our answer for this particular problem. The voltage VO equals 3.55 volts, and that's going to be the voltage flowing through this 4K resistor right here. Okay, so we've successfully solved this problem. If you have any questions, please leave them down below.